Okay, so this is part 2, parametric and vector accumulation. So here we're going to be basically applying the calculus. Okay, so really quick, suppose a particle moves along a path in a plane so that its velocity is given as a vector with two parts, x and y. Then the displacement from A to B is given by a vector, and that vector, you take the integral of the velocity and the integral of the y component of the velocity from A to B. So you notice that the displacement, your answer is actually going to be a pair. The preceding vector is added to the position at a time t equals a to get the position at time t equals b. So keep this in mind. You'll see this in action in just in one of the examples. And then the distance traveled, you basically, from t equals a to t equals b, is the arc length. And you integrate the speed of that vector. And the way that you get the answer is you integrate, you use the arc length equation, okay? Using the velocity of x plus the velocity of y, square them both. So this first example, just FYI, before I forget, this is the same thing that we were doing before. When you're asked for acceleration, you're going to find the derivative of velocity. If you want the position, you're going to integrate velocity, right? So it's the same as before, except we're going to be doing it twice. So we're going to do a lot of this in the calculator, so make sure that your calculator, your graphing mode is in parametric, and you are in radian mode in order to solve parametric equations. So here's our first example. An object moving along a curve in the xy plane has the position x of t, y of t at a time t with the velocity given dx dt, so the derivative is t sine t, and then the derivative of y is cosine t squared. So we're not given the position, we're given the velocity. At t equals 2, the object is at a position of 1, 4. So our first example says find the acceleration vector for the object. So we know that the derivative of velocity is equal to the acceleration, correct? Which is basically taking the second derivative of the position function. But we are given the velocity, so we just have to make sure that we take the derivative of velocity to get to acceleration. But here, like I told you, we're going to be doing this in the calculator. In order to do this in the calculator, believe me, through about a half hour of trial and error, let me just clear my history, and I'm going to show you how to do this in the calculator. So the first thing we're going to do is put your calculator in parametric graphing mode, and a few key things. Right now I'm just graphing the derivative of x and the derivative of y because that's what's given. So I know I'm graphing it under x1 and y1, but keep in mind those are not the position functions. So a few things when you are plotting these, I'm just gonna, you know what, let me just delete all, just to show you exactly how to do this. So I'm in parametric. x1, you see how it says t sine of t? You can't just plug it in like that. You actually have to either put the t, so put your variables in parentheses, or actually use the multiplication button. But just put your variables in parentheses, it will work every single time. If you don't do that, it's going to say function is undefined. Okay, so t sine of t, and then my y is going to be cosine of t squared. Now you could, just for, you know, staying true to keeping our variables in parentheses, I just did that, and you'll notice that when you graph it, it looks a little different, but it'll be accurate. I really don't care too much about the graph right now because I just want to use these functions in order to evaluate. So I'm going to go back to my calculator screen, okay, and I want to evaluate the second derivative of the position, which is the derivative of the velocity. And I plotted the derivative of the velocity. So I want to find the derivative. My variable is t because it's parametric. The derivative of the velocity for the object at the value t equals 2. And I want to find the first derivative because I want to find acceleration from what I had, which is the velocity. So here, to input which function we're using to derive, you just press vars, and you'll notice that x1 and y1 are both in here. I want to start off with my x component. My t is my variable. Press enter. There's your answer. So my x double prime of 2 is going to be 0.077. Take 3 decimal places always when you're calculating. And I'm going to do the same thing for y. So I'm going to go to menu, calculus, derive at a point. My variable is t, my value is 2. But this time, when I press vars, I want my y1 of t. Press enter, and there's your y component. 3.027, remember 3 decimal places. And there it is. There's my acceleration vector at t equals 2. Okay? Now next we want to write the equation of the tangent line to the curve at the point where t equals 2. So in order to write the tangent line, we need 2 things. We're going to need the slope, and we're going to need the point, the xy. And we know at t equals 2, our point was 1, 4. Okay? Now remember, we're using point slope form, but I still need to find my slope. So if you remember, your slope is dy dx, right? So your slope is the derivative of y over the derivative of x at t equals 2. So here, my y prime of 2 over my x prime of 2. So basically you're going to evaluate your derivative function, which guess what? They already gave that to us. So my y prime of 2 is going to be cosine of 2 squared, which is 4, divided by x prime of 2, so that's going to be 2 times sine of 2. And you can either plug that into the calculator or let the calculator derive it for you using what you have inputted. So let me show you what I mean. So basically we're going to take our y function that we've inputted. So I'm going to do, let me escape that. I want to divide. Oops, sorry. So control divide to get my division number. And I'm going to input my vars, my y of 2 over vars of x of 2. Press enter, and you get that answer. And guess what? If you plugged in cosine of 4 divided by 2 sine of 2, you're going to get that same exact answer. So this is negative 0.359, and that is my slope. So now that I have my slope and I have my point, I can just plug in y minus my y value, which is 4, equals negative 0.359 of x minus 1. And if they wanted slope-intercept form, you know how to simplify this to get slope-intercept form. Alright, now we want to find the speed of the object at t equals 2. So remember that the speed is a single answer. Okay? And basically to find the speed, which is right here, not the integral, but that right there was our speed. So this right here is going to basically give us our speed. Now when you integrate the speed, you get the distance traveled. But that's our speed right there. So my speed is going to be my velocity function, which I actually have. The speed of the velocity function at t equals 2. So I'm just going to take x prime of 2, square that, plus y prime of 2, square that, and if you do this in the calculator, remember we already have these functions stored as the velocity functions, so I just have to take the square root of x of 2, let's put this in parentheses so I don't mess up, square that, plus my y function, which is, again, let's put the whole thing in parentheses, of 2 squared, and you get 1.933. Now here we don't have units, so that's why I haven't been putting any units, but of course if you're given units, you have to put those down. Okay? Moving on. Now we're actually going to start integrating. So let's find the displacement of the object from t equals 2 to t equals 7. So here's my displacement. I'm going to integrate the velocity function from 2 to 7 and integrate the velocity function of y from 2 to 7. So again, my answer is going to be a pair. It's easy if you kind of remember those. Okay, so your answer is going to be a pair. So my displacement is going to be the integral of 2 to 7 of x prime of t and the integral of 2 to 7 of y prime of t. Now keep in mind they gave us x prime, they gave us y prime. So, and I've already plugged those into my calculator, so I just need to integrate from 2 to 7 t sine t, and from 2 to 7 cosine of t squared dt dt, okay? So here is what we're going to do. Just go to menu, calculus, but this time we're going to find a numerical integral. And we're going to go from 2 to 7 of vars, my x, of t, and of course you have to put dt in here, solve, and there's my first answer, and I'm going to do the same thing for my second answer, 2 to 7 vars of this time y, t, dt. Alright, so I'd have to work a little bit. But those are my two answers right there. So I'm going to plug those in. So my displacement is negative 6.362. Remember, 3 decimal places is the best for the AP exam. 0.097. So basically this says that it moved 6 units left and this many units up in 5 seconds from t equals 2 to t equals 7. So in 5 seconds, it moves 6 units left and 0.097 units up from its original position. Alright, finding the distance traveled. So recall, distance traveled. It's going to be a single answer, and we're going to integrate the velocity from t equals 2 to t equals 7. So remember that this is also known as arc length. Okay? So how far did it go along the curve? So we're going to integrate from 2 to 7, the velocity function, which basically is the same, or the speed of the velocity function, from 2 to 7 of x prime of t squared plus y prime of t squared. And again, I'm going to use my calculator for this whole entire thing. So I'm going to integrate, menu, calculus, integral from 2 to 7 of the square root. And you see why it's so important to store those functions at the beginning. So vars x of t squared plus vars y, remember to put those in parentheses so that it squares the whole thing, t squared, and don't forget your t to represent what you are integrating in terms of. Wow, can you imagine if it's taken the calculator that long, how long it would take us to do this? So our answer is going to be 13.229. Now, we're not putting units, but remember distance traveled is going to be length units if we had units. So one single answer for distance traveled. So find the position of the object at time t equals 1. Okay? So now we are finding a different position. Now we were told that at t equals 2, the position was at 1, 4. The question is at t equals 1, the position is where? So we have to take the information that is given to us, or where the position started, because this was the start, and we are going to add the displacement of each component based on its velocity. So basically, x of 1, y of 1 is going to be found out by simply taking the start of x, which was at 1, and adding it to the integral from 2 to 1, because this is where it started and we are going to 1, so we're kind of going back in time of the velocity function, and same thing for the y value. So it's going to be 4 plus the start, which was at 2 to 1 of the y, of the velocity of y, or the derivative of y. And again, this is a simple thing that you can do in the calculator as long as you have everything stored. So I'm going to go 1 plus the integral from 2 to 1 of my velocity function, t dt. Okay, so that's my x component. And then 4 plus the integral from 2 to 1 of my y function, my velocity of y, t dt, enter. So there's my x and there's my y. So my position at 1 second is 0.440 units left and 4.443 units up. Okay, so this is a very good calculator for your response question. You probably won't have all of these parts because that's a lot, but you'll have portions of it. Okay, example 2. This is also a calculator example. An object moving along a curve in the xy plane has the position x of t, y of t at a time t greater than or equal to 0, with dx dt being 2 sine of 2 squared. The derivative dy dt is not explicitly given yet, so we may have to find that. And at time t equals 2, the object's position, so the initial position is 3, 5. Find the x-coordinate of the position of the object at t equals 4. So we're finding the position. The same thing that we did here, but the only difference is that we're focusing at just the x, which makes sense because we actually don't have the y yet, so there's no way for us to figure it out yet. Okay, so we know that basically where is this thing at x of 4? So they gave us the starting position. They told us that at t equals 2, our x is 3. So our start is going to be at 3 plus the integral from the start to 4 of our velocity function of our object. So you have to go ahead and plug this in. It's the same exact thing, but now we gotta go back and delete our other function, or I can plug it into x2 here. So because I don't care about the graph, so I'm gonna plug in x2 as 2 times sine of t squared. Okay, so this calculator, since I don't have something for y right now, it's not going to let me, so I'm just going to plug something in for y just so that I can use my vars, my x2, okay? So it doesn't mean that what I just plugged in is correct. So here we have 3 plus the integral from 2 to 4 of my vars. This time I want to go to x2, okay, of t. So that's why it's a good idea to kind of erase everything from problem to problem just so that you don't mess up. But if you're good with it, then don't worry about it. If you can keep up with all the different numbers for your functions. So 2.884. Now no units given, so that's all I'm going to put down right here. So the position is at 2.884 for the x-coordinate at time equals t, at t equals 4. All right. At time t equals 2, this may be the last problem we can do in this video, and we'll finish the last 2 tomorrow. So I gotta go pick up my kids. So at time t equals 2, the value of dy dt, so they give us dy dt is negative 6. We're going to write an equation for the line tangent to the curve at the point x of 2 and y of 2. Okay? So keep this in mind. What are they telling you? That when t equals 2, the value of the derivative is negative 6. So remember, when we're writing an equation line, we need the slope and we need a point. Now the slope, how do we solve for the slope? We have to get dy dx at t equals 2 because that's what they want. They want the slope at t equals 2. And the point, they actually already gave us the point at t equals 2. The point at t equals 2 was 3, 5. They gave it to us in the previous page. So now I just need to find the slope. So I'm going to move over here. So m is dy dx at t equals 2. So it's basically y prime of 2 divided by x prime of 2. Now, what is y prime of 2? They never gave us a derivative, a dy dt. But what they did give us is that at 2, y prime is negative 6. So basically, y prime of 2 is negative 6. And down here, x prime of 2, they told us that x prime is 2 sine 2 squared. So I just need to plug in 2 into t. So it's 2 sine of 4. And you can clean this up. Now, if this was a calculator problem, you'd want to, evaluate this to get an actual number. But if it was not, then you would just clean this up, so you'd end up with negative 3 sine of 4. A little easier way or cleaner way that we can write this if this was a non-calculator problem. Can we get this out of the denominator by calling it negative 3 cosecant of 4? Okay, now I think that this would be more than enough, but this is a little bit nicer. So now what's our equation? Okay, let's pretend we didn't have a calculator for this. So what's our equation is going to be y minus 5 equals the slope, which is negative 3 cosecant of 4, x minus 3, using our points. Alright, you guys can probably finish this. Find the magnitude of the velocity vector at time t equals 2. So this is basically saying find the speed, right? So it's the velocity of vector at 2, the speed of the velocity vector at 2. So if you plug that into the calculator, it's x prime of 2 squared plus y prime of 2 squared. And then here, x prime of 2, we already know that x prime of 2 is going to be 2 sine of 4, and we need to square that. Plus, we know y prime of 2, they gave it to us up here, it's negative 6 squared. And do this whole thing in the calculator. Be careful of rounding. Don't do individual parts and then add them up and then take the square root. Try to plug it all into the calculator and get the answer. Now this last question, it's not so much difficult as it is just you have to do some side work. Okay? It says find the acceleration vector, and we know that to find the acceleration vector at 4, we have to find the derivative of the velocity vector at 4, which basically means that we need the double derivative of the initial position at 4 and the second derivative of the y vector at 4. So we have the velocity of x, so we can easily find the derivative of this, of the velocity of x, since we already have v. But here, the question is, how do we get the acceleration if we don't even have the velocity function? So it's going to take some algebra. We'll finish this together in class. Okay, I will send a remind with homework problems that go along with this unit, but it's going to be after I come back home.